July 18 1943, Yokosuka Naval Arsenal, Japan. Lieutenant Commander Hiroshi Nakamura stared at the shattered remains of the American proximity fuse spread across his workbench, illuminated by the harsh light of a single bulb. Outside his laboratory window, naval officers gathered in hushed conversation, their faces etched with growing concern. The device before him, a technological marvel that had decimated Japanese aircraft with unprecedented precision, represented not just an American victory, but a glimpse into an industrial and scientific capability that would ultimately seal Japan's fate in ways none of them yet fully comprehended. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The proximity fuse, or VT fuse as Americans coded it, had revolutionized anti-aircraft defense virtually overnight. In the past 6 months, American warships equipped with these new weapons had increased their effectiveness against Japanese aircraft by over 500%, where before it took an average of 2,000 conventional shells to bring down a single aircraft. Now it required fewer than 30. Japanese pilots had returned with harrowing stories of invisible walls of death, shells that seemed to know where they were, explosions that needed no direct hit to tear wings from fuselages. The recovery of intact fuses had become a matter of national urgency. 3 weeks earlier, a damaged American 5-inch shell had been found unexploded in the wreckage of a destroyer near Guadalcanal. At tremendous risk, Japanese ordnance experts had disarmed and transported it back to Japan, handling it like a sacred artifact. Now that precious technological prize sat disassembled before Nakamura. Unlike the military officers celebrating this intelligence coup, his expression betrayed no triumph, only a deepening apprehension that knotted his stomach and tightened his jaw. As Japan's leading electronic engineer with a doctorate from Tokyo Imperial University, he understood with painful clarity what his nation was truly facing. "Impossible," he whispered, picking up the miniaturized vacuum tube with trembling fingers. "This cannot be mass-produced. Not by us. Not now. Perhaps not ever." His assistant, Yoshiro Tanaka, looked up from his notebook where he had been sketching diagrams. "What do you mean, Sensei? We have the enemy's weapon right here. We can see how it works." Nakamura set the tube down carefully. "Seeing is not the same as building, Tanaka-san. Look at this vacuum tube. It's the size of my thumbnail. The smallest we can reliably manufacture is 3 times this size, and each of these fuses contains 5 of them." He gestured toward the rest of the components. The precision required for these mechanical components, the materials science behind this rugged capacitor design, the waterproofing that allows it to survive the G-forces of firing yet still function perfectly. He shook his head slowly. "This is not just a weapon, it's a declaration of industrial superiority." Unlike many of Japan's military leaders, Nakamura had spent 4 years studying electrical engineering at the Massachusetts Institute of Technology in the 1930 seconds. He had walked through the sprawling electronics factories of the Radio Corporation of America, where automated assembly lines produced vacuum tubes by the thousands per hour. He had toured the Bell laboratories where American scientists with seemingly limitless resources pursued research that Japanese institutions could only dream of undertaking. He had witnessed firsthand the vast gulf between Japanese and American electronics manufacturing capabilities. While Japan's best factories laboriously produced radio equipment by hand, with skilled workers hunched over benches with magnifying glasses, America was pioneering mass production techniques that turned complex electronic devices into commonplace consumer goods. "Do you know what RCA's annual production of vacuum tubes was in 1941? Nakamura asked, not expecting his assistant to know. "Over 100 million units. Our entire national output was less than 10 million, most of which were simple designs for civilian radios." "These miniaturized, ruggedized tubes?" He pointed to the delicate glass component. "We have no factory capable of making these at scale. Not one." What Nakamura understood, what he could not make his superiors comprehend despite his repeated warnings, was that modern warfare had evolved beyond the realm of courage and tactical brilliance. The new battlefield advantage lay in industrial capacity, scientific infrastructure, and technological innovation that required decades of development and investment to achieve. The proximity fuse represented something few Japanese officials grasped: the weaponization of America's consumer electronics industry. The same assembly lines that had produced radios and telephone equipment for American homes had been rapidly converted to manufacture these sophisticated weapons. The same engineers who had designed broadcast equipment and household appliances now created instruments of war with devastating effectiveness. The Americans began developing these in 1940, Nakamura continued, almost speaking to himself now. In just 2 years they went from concept to mass production. They're manufacturing them at a rate of thousands per day now. Thousands. Each one a marvel of miniaturization and precision engineering. The mathematics of technological warfare that now confronted Japan were stark and unforgiving. According to intelligence reports, American factories were producing proximity fuses at rates that seemed fantastical to Japanese officials. The Johns Hopkins Applied Physics Laboratory coordinated a manufacturing effort spread across multiple companies and regions, each specializing in specific components that were then assembled with mechanical precision. By comparison, Japan's entire electronics industry consisted of a handful of companies operating primarily with manual assembly methods. The gap wasn't merely one of volume but of fundamental capability. Japan in 1943 simply lacked the industrial base, the specialized machinery, the quality control systems, and the trained workforce needed to produce such advanced electronic weapons. Nakamura had attempted to communicate this reality to Naval Command just yesterday. His audience had been a room of stern-faced admirals, men whose understanding of technology extended little beyond the mechanical systems they had studied decades earlier at the Naval Academy. "With all respect, Admiral Kaneda," he had said, addressing the head of naval weapons development, "reverse engineering this fuse design is not the primary challenge. The real obstacle is manufacturing capability." "Explain yourself, Commander," Kaneda had replied, his voice sharp with impatience. "Even if we perfect a design based on this American model, which would require components we currently cannot manufacture domestically, we lack the industrial capacity to produce them in meaningful quantities. At our current capabilities, we might manage 5 to 10 units per day, with high failure rates. Intelligence suggests the Americans are producing over 2,000 per day. The disparity is insurmountable in the near term." His assessment had been met with stony silence, then dismissal. "Find a way, Commander. Japanese ingenuity has overcome obstacles before. The Emperor expects solutions, not excuses." Now, back in his laboratory, the full weight of that impossible expectation pressed down on him. Nakamura had been ordered to develop a Japanese proximity fuse within 6 months, with production to begin immediately thereafter. It was a task he knew to be impossible, yet saying so again would be seen as defeatism, perhaps even treason. The truth that haunted Nakamura was that this technology represented not just a single weapon, but an entirely different level of industrial and scientific capability. The Americans hadn't just created a better fuse, they had demonstrated mastery of an entire technological domain that Japan had barely begun to explore. "Tanaka," he said quietly, "what do you know about the American industrial base for electronics?" His assistant looked up, surprised by the question. "Only what I've read in technical journals, Sensei. They have large factories, primarily on their east coast." Nakamura nodded. "Before the war, I toured the RCA manufacturing facility in Camden, New Jersey. It employed over 9,000 workers in a single factory. The entire building was dedicated to radio and electronics production. They had automatic testing equipment that could verify hundreds of vacuum tubes per minute. Their research division had more engineers than our entire naval electronics department." He picked up the proximity fuse's safety and arming mechanism, a marvel of miniaturized mechanical engineering. This single component requires precision machining to tolerances of 5/1000ths of an inch. Do you know how many metalworking shops in Japan can achieve such precision consistently? Perhaps 3. All of them already operating at maximum capacity for other critical war materials. What Nakamura couldn't bring himself to say aloud was that this technology gap reflected something more fundamental than just industrial capacity. It represented decades of American investment in scientific education, corporate research laboratories, standardization practices, and manufacturing knowledge, an entire ecosystem of technological innovation that Japan had only begun to develop in the 1930 seconds. The proximity fuse had not emerged from nowhere. It built upon America's leadership in vacuum tube technology, broadcast engineering, and consumer electronics. It leveraged industrial processes refined through decades of mass-market production. It utilized quality control methods pioneered by American corporations and standardized components developed for civilian applications. Japan had neither the time nor resources to replicate this ecosystem during wartime. The technological gap could not be closed by willpower or sacrifice, or even exceptional individual brilliance. It was systemic, structural, and, Nakamura now realized with growing dread, potentially decisive for the war's outcome. Later that evening, as darkness fell over Yokosuka Naval Arsenal, Nakamura remained at his workbench, making detailed drawings of each component. His assistant had left hours ago, but sleep would not come for the commander, not with the weight of impossibility pressing down on him. A soft knock at the laboratory door roused him from his concentration. Captain Sadao Ito, his former classmate and now head of naval intelligence for the home islands, entered quietly. "Still at work, Hiroshi? It's nearly midnight." Nakamura set down his pencil. "The problem does not resolve itself because the hour grows late, Sadao." Ito pulled up a stool. Unlike most naval officers, he had spent time abroad as well, serving as an attaché in Washington before the war. He understood technology and America in ways many of their colleagues did not. "Tell me honestly," Ito said, his voice low. "Can we replicate this weapon?" Nakamura met his friend's gaze. Between them, at least, there could be truth. "No, not in any meaningful time frame or quantity. The industrial prerequisites simply don't exist in Japan." He gestured to the disassembled fuse. "This isn't just a clever device, Sadao. It's the culmination of an entire technological society we don't possess. The Americans haven't just created a better weapon, they're fighting a different kind of war than we are. An industrial war where factories matter more than fleets, where production capacity ultimately means more than the courage of individual warriors." Ito's face remained impassive, but his eyes reflected understanding. "And our leadership refuses to see this. They see what they want to see, what they need to see to continue believing victory is possible. They imagine this is merely a matter of discovering the secret, as if American superiority in radar or proximity, fuzes or aircraft engines, comes down to a single brilliant idea we haven't yet had." Nakamura spread his hands in frustration. "But there is no secret formula. The proximity fuse works on principles we already understand. The difference is that Americans can manufacture 5 complex electronic components in a package the size of an egg, ruggedized to withstand 20,000 grams of acceleration, with a self-destruction feature, at a rate of thousands per day. We cannot. And we cannot create the industrial capacity to do so in the middle of a war where our factories are already operating beyond their limits." Ito nodded slowly. "I've received reports from our attachés in Switzerland. American war production exceeds even our most pessimistic pre-war estimates. A single American company, this Western Electric, is producing more electronics equipment each month than our entire nation. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us." Now back to the story. "Western Electric?" Nakamura repeated softly. "Yes. I visited their Hawthorne works outside Chicago, 35,000 workers in a single facility. Sadao, producing telephones and switching equipment with automated machinery that operated with precision our craftsmen can only dream of achieving. And that was in peacetime, before they converted fully to war production." The two men sat in silence for a moment, the implications hanging heavy in the air between them. Japan had begun the war believing its spiritual strength, martial tradition, and fighting spirit would overcome American material advantages. But the proximity fuse on the table between them told a different story, one of scientific advancement, industrial capacity, and technological superiority that no amount of courage could counterbalance. "There's more," Ito said finally. "Intelligence reports from Germany suggest the Americans are working on other electronic weapons systems, guided bombs, automated targeting systems, something called electronic countermeasures to jam our radars." Nakamura wasn't surprised. The proximity fuse was likely just the beginning, the first glimpse of an accelerating technological gap that would only widen as the war progressed. "What will you tell Admiral Kaneda?" Ito asked. "The truth, though in terms he might accept. I'll propose a Japanese alternative, a simplified proximity fuse using technology we can actually manufacture. It will be less effective, larger, and we can produce perhaps 50 per month if we're fortunate. I'll emphasize that this approach plays to our strengths rather than attempting to copy American methods directly." Both men understood this was merely a face-saving gesture. A Japanese proximity fuse produced in such limited quantities would make no meaningful difference in the air defense capabilities of the fleet. By the time even this compromised version could reach production, thousands of American aircraft would be equipped with even more advanced electronic systems. Nakamura returned to his quarters just before dawn, exhausted but unable to rest. Through his small window, he could see the first light touching the waters of Tokyo Bay, where warships lay at anchor, ships that now seemed terribly vulnerable in light of what he had learned. The proximity fuse represented something beyond a tactical advantage. It symbolized a fundamental shift in the nature of modern warfare, from a contest of courage and tactical brilliance to one of scientific advancement and industrial capacity. The samurai tradition valued the perfection of the warrior. America had perfected the factory system instead. As an engineer, Nakamura could appreciate the elegant solution the Americans had devised: a miniature radio transmitter and receiver that detected an aircraft's presence and detonated the shell at the optimal moment. As a Japanese naval officer, he could only despair at what it represented for his nation's future. In the coming months, his worst fears would be confirmed. While Japanese engineers struggled to produce even prototype versions of proximity fuses, American ships and land-based artillery deployed them in ever-increasing numbers. By early 1944, American destroyers were routinely shooting down multiple aircraft with astonishingly few shells expended. At Saipan in June 1944, the Japanese mounted a desperate aerial counterattack against the American invasion fleet. Over 300 aircraft were committed to the battle, a substantial portion of Japan's remaining naval air strength. American ships, now extensively equipped with proximity-fused anti-aircraft shells, created a wall of lethal steel that Japanese pilots could not penetrate. Fewer than 30 American sailors died. Japan lost over 240 irreplaceable aircraft and experienced pilots. American war correspondents dubbed it the Great Marianas Turkey Shoot. For Japanese naval aviators, it represented the collapse of their ability to threaten American naval forces. For Nakamura, watching the reports come in from his laboratory in Yokosuka, it confirmed everything he had feared since first examining that captured proximity fuse nearly a year earlier. The technological gap that had seemed so daunting in his laboratory had manifested as catastrophic defeat at sea. Japan had lost not because its pilots lacked courage or skill, indeed. They had displayed both in abundance, but because industrial capacity and technological superiority had rendered such qualities increasingly irrelevant. The proximity fuse was not merely a weapon, it was a harbinger of a new era, where nations would be measured not by the spirit of their warriors, but by the sophistication of their laboratories and the output of their factories. The battle for the Pacific was being decided not just on remote islands and vast oceans, but on assembly lines in places like Camden, New Jersey, and Hawthorne. Illinois, places most Japanese military leaders couldn't find on a map, yet which were proving more decisive than any battlefield. As autumn approached in 1944, Nakamura was summoned to Imperial headquarters in Tokyo. The mood had changed dramatically from the previous year. Gone was the dismissive confidence, replaced by a grim resignation as reality increasingly intruded on Japan's strategic calculations. Admiral Kaneda, who had once dismissed Nakamura's warnings, now listened intently as the engineer briefed a roomful of senior officers on America's growing electronic warfare capabilities. The proximity fuse had been just the beginning. American forces now deployed radar sets in numbers Japan couldn't hope to match, electronic navigation systems that allowed precision bombing through cloud cover, and jamming devices that blinded Japanese defenses. The technology gap is not merely quantitative but qualitative, Nakamura explained, his voice steady despite the gravity of his assessment. We are not simply producing fewer electronic systems than the Americans. We are producing fundamentally less sophisticated systems. This gap cannot be closed through greater effort or sacrifice. It represents decades of industrial development and scientific advancement that cannot be replicated in wartime. The faces that stared back at him were solemn, many nodding in reluctant agreement. What had seemed unpatriotic defeatism a year ago was now recognized, too late, as prescient analysis. As he concluded his briefing, Nakamura offered the only recommendation he could in good conscience provide. Japan must seek terms while it still retained some bargaining position. The alternative was continued resistance against an opponent, whose technological superiority would only increase with time. His words were met with silence. While many officers present might privately agree, such a recommendation remained politically impossible to voice publicly. Japan would continue fighting, not because victory remained possible, but because the machinery of war, once set in motion, proved difficult to stop even in the face of certain defeat. Nakamura returned to his laboratory that evening, the weight of futility heavy on his shoulders. On his desk lay the prototype of the Japanese proximity fuse, larger than its American counterpart, less reliable, and produced in quantities so small as to be militarily insignificant. It represented the best Japan's electronics industry could achieve, yet remained hopelessly inadequate against the flood of American technology now deployed across the Pacific. The lesson of the proximity fuse would outlast the war itself. In the decades to come, Japan would rebuild itself not around military power but technological and industrial excellence. The nation that had once believed in the supremacy of fighting spirit would become a global leader in electronics manufacturing, eventually producing the precision components it had been unable to match during the war. But that future lay beyond the horizon of defeat that now approached with terrible certainty. For Nakamura and his colleagues, the proximity fuse had revealed a truth that Japanese military doctrine had refused to acknowledge. In modern warfare, industrial capacity and technological sophistication would prove decisive. The nation that could not only design but mass-produce complex electronic systems would ultimately prevail against even the most determined opposition. The proximity fuse, that small marvel of American engineering that had crossed his workbench in 1943, had foretold Japan's defeat more clearly than any battle, not because Japanese engineers couldn't understand it, but because Japanese industry couldn't replicate it. In that gap between comprehension and capability lay the true story of the Pacific War's outcome, written in vacuum tubes and circuit boards, rather than bullets and blood. As the winter of 1944 descended upon Japan, Nakamura's laboratory became increasingly isolated from the larger war effort. Resources that had once been allocated to his proximity fuse research were diverted to more immediate concerns: the defense of the Philippines, the fortification of Iwo Jima, the desperate scramble to produce enough aircraft to replace catastrophic losses. The engineer found himself with more time to analyze intelligence reports and technical journals smuggled through neutral countries. Each document reinforced his growing understanding of America's technological acceleration. The proximity fuse, he realized, was not merely a single innovation but part of a systematic revolution in warfare, one driven by an unprecedented partnership between America's universities, industries, and government. One cold December morning, Nakamura received an unusual visitor. Dr. Hideki Yukawa, Japan's leading theoretical physicist and a professor at Kyoto Imperial University, arrived unannounced at the Naval Arsenal. "Professor Yukawa," Nakamura said, bowing deeply, "this is an unexpected honor." The physicist's presence at a naval installation was highly irregular. As a civilian academic with no direct military role, His visit suggested matters of extraordinary significance. "Commander Nakamura," Yukawa replied, returning the bow. "I've read your analysis of American electronic warfare capabilities. Your insights align with concerns in my own field." Once alone in Nakamura's office, the physicist spoke with careful precision. "I've been asked to consult on a matter of national importance. There are rumors concerning reports from our attachés in Sweden about an American scientific project of unprecedented scale." Nakamura felt a chill that had nothing to do with the winter air. "What kind of project?" "They call it the Manhattan Project. Details are sparse, but its scale is apparently enormous. Multiple facilities, each larger than entire Japanese industrial complexes, tens of thousands of workers, budgets that exceed the cost of our entire navy." Yukawa hesitated. "The reports suggest it involves nuclear physics." The implications hung in the air between them. Japan's own nuclear research program was theoretical and minuscule, comprising a handful of physicists working with limited resources. If America was applying its industrial might to nuclear weapons development, our government needs realistic assessments, Yukawa continued. Not what they wish to hear, but what they need to understand. Your analysis of the proximity fuse technology gap was prescient. We need similar clarity regarding this new threat. Nakamura considered his response carefully. "Professor, when I examined the American proximity fuse, I wasn't just seeing a weapon. I was seeing the output of an entire technological ecosystem we lack. The miniaturization, the mass production capability, the integration of scientific research and industrial capacity." He spread his hands. "If the Americans are applying that same system to nuclear physics, combining their scientific expertise with industrial scalability, then any gap between our capabilities would be even more pronounced than with conventional weapons." Yukawa nodded grimly. "That aligns with my assessment. Our nuclear research is purely theoretical. We lack even the basic industrial infrastructure to purify uranium or produce heavy water in meaningful quantities." Over the following weeks, Nakamura and Yukawa formed an unusual partnership, combining their expertise to assess fragmentary intelligence about American scientific and industrial mobilization. The picture that emerged was sobering beyond their initial estimates. American science and industry had achieved a synergy that Japan couldn't hope to match. The proximity fuse, radar, sonar, electronic fire control systems, these were just the visible manifestations of a deeper transformation. America had converted its consumer industrial base into a weapons production system, with a speed and completeness that defied conventional understanding. In January 1945, they presented their findings to a select group of senior officials. The meeting took place not in a military headquarters, but in a private room at the Imperial Hotel in Tokyo, away from the bombing raids that now regularly struck the capital. "Gentlemen," Nakamura began, "the technological disparity between Japan and America is not merely a matter of production volumes or resource availability. It is fundamentally about industrial systems and scientific application." He used the proximity fuse as his primary example. American industry didn't simply build a better anti-aircraft shell. They transformed their consumer electronics industry into a weapons production system. The same factories that once made radios for civilian homes now produce electronic warfare systems that our pilots cannot counter. Yukawa followed with his assessment of American scientific capabilities. Their university system produces more physics and engineering graduates in a single year than Japan has trained in the past decade. Their industrial laboratories employ more researchers than our entire scientific establishment. The room grew silent as the implications became clear. Japan was not merely losing a war of attrition. It was fighting against an opponent whose technological capabilities were advancing at an accelerating rate, while Japan's own development had stagnated or regressed under bombing and blockade. One admiral, his face impassive, asked the question they had been anticipating: "What does this mean for Japan's capacity to continue resistance?" Nakamura met the man's gaze directly. "It means that time works against us. Each month that passes widens the technological gap. American weapons systems grow more sophisticated, while our own development programs struggle to maintain existing capabilities." He pointed to reports of American aircraft now appearing over Japan. The B-29 Superfortress represents technology we cannot currently match. Its electronic systems, its high-altitude capabilities, its fire control computers, these are beyond our present industrial capacity to counter effectively. What Nakamura couldn't share, what remained classified even from this senior group, was intelligence suggesting the Americans were preparing these advanced aircraft for a new kind of mission, potentially related to the Manhattan Project that Yukawa had mentioned. As the meeting concluded, Vice Admiral Takejiro Onishi, architect of the Special Attack Units, approached Nakamura privately. Unlike many of his peers, Onishi had a sophisticated understanding of technology and its limitations. "Your assessment confirms what some of us have suspected," he said quietly. "We are not merely fighting the Americans. We are fighting their industrial system, their scientific establishment, their technological infrastructure." Nakamura nodded. The proximity fuse revealed this truth more clearly than any battle. "Admiral, we can understand how it works, even design our own versions, but we cannot produce them in quantities that matter militarily. That gap exists across virtually all advanced weapons systems." Onishi's expression remained carefully neutral. "And yet we must continue to fight with what we have." "Of course, Admiral. I merely suggest that our strategy must acknowledge these realities rather than deny them." The implications of their conversation remained unspoken but understood. Japan's strategy had shifted toward increasingly desperate measures: kamikaze attacks, civilian mobilization for homeland defense, plans to resist invasion with bamboo spears if necessary. These were not the actions of a nation with a technological parity, but of one attempting to offset overwhelming material disadvantage with sacrifice and spiritual resolve. As spring arrived in 1945, Nakamura received new orders. His proximity fuse research facility was to be relocated inland, away from the increasing American air raids on coastal installations. The move reflected a larger pattern of dispersal, as Japan's military production went underground, into caves and tunnels, scattered across the countryside to avoid the precision bombing that had devastated urban industrial centers. Before departing Yokosuka, Nakamura received permission to visit the naval air station at Atsugi, where returning pilots shared their experiences facing American defenses. What he heard confirmed everything his technical analysis had suggested. "The Americans create a wall of fire around their ships," one young pilot explained, his eyes haunted by memories of comrades lost. "Their shells explode without hitting anything. Just being near their ships means death." Another veteran with burn scars covering half his face described attacks against B-29 formations. "Their electronic countermeasures blind our radars. Their defensive fire seems to know where we are, even in clouds. It's as though they see without eyes, hear without ears." These were the real-world manifestations of the technology gap Nakamura had identified through his laboratory analysis. American proximity fuses, radar guidance, electronic jamming systems, components of an integrated electronic battlefield that Japan could comprehend but not replicate. At his new facility, a converted textile mill in the mountains of Gunma Prefecture, Nakamura found himself with reduced resources but increased autonomy. Rather than continuing the futile attempt to mass-produce proximity fuzzes, he redirected his team toward electronic countermeasures, simple jammers that might give Japanese aircraft some chance against American radar systems. It was during this period that Nakamura reconnected with an old colleague from his MIT days. Dr. Reginald Turner had been his American research partner in electrical engineering, now working at the MIT Radiation Laboratory on military electronics. Their communication came through the most unlikely of channels, a Swedish diplomat who had studied with both men before the war. The letter, carefully worded to pass censors, contained a message that chilled Nakamura to his core. "Our mutual interest in radio wave propagation has advanced considerably. The project employs 130,000 people across multiple facilities, with a budget equivalent to building 8 battleships per year. The energy release from successful tests exceeds anything previously achieved by several orders of magnitude." To most readers, these words would seem innocuous, perhaps referring to some advance in radar technology. To Nakamura, with his background in physics and electronics, the meaning was unmistakable. The Manhattan Project had succeeded. America had developed atomic weapons. His hands trembling, he immediately sought secure communication with Professor Yukawa. Their subsequent meeting, held in a remote mountain inn, confirmed his worst fears. Japan's rudimentary nuclear program had made virtually no progress, while America had apparently succeeded in weaponizing nuclear reactions. The industrial gap we identified with proximity fuses was a harbinger, Yukawa said quietly. The same pattern applies to nuclear technology, but with even greater disparity. We lack the industrial capacity to produce fissionable materials in significant quantities, even if we had the theoretical knowledge. Nakamura nodded grimly. The proximity fuse required electronics manufacturing capabilities we didn't possess. Nuclear weapons require industrial infrastructure so far beyond our current capacity that the comparison becomes meaningless. In that moment, both men understood that Japan faced not merely military defeat, but a technological revolution that had left their nation behind. The proximity fuse had been just the first glimpse of this new reality, a warning sign they had recognized, but that Japan's leadership had failed to fully comprehend. By July 1945, as American forces prepared for the invasion of Japan's home islands, Nakamura found himself summoned to Tokyo one final time. The city he had known was barely recognizable, reduced to rubble by precision bombing that targeted industrial and military facilities with devastating accuracy. The meeting took place in a bunker beneath the Imperial Palace grounds. Present were representatives from the Army, Navy, and civilian government, a cross-section of Japan's leadership, facing the prospect of imminent defeat. Commander Nakamura, began Lord Keeper of the Privy Seal Kido, effectively the Emperor's chief advisor. Your technical assessment of American capabilities has proven prescient. We need your candid evaluation of Japan's technological position and prospects for continued resistance. Nakamura had prepared for this moment, knowing that absolute honesty was now both possible and necessary. The technological gap between Japan and America has widened rather than narrowed since the war began. American electronic warfare capabilities, which I first identified through analysis of their proximity fuses, have evolved into integrated systems that our forces cannot effectively counter. He laid out the stark realities in clinical detail. American radar could detect Japanese aircraft at ranges that made surprise attacks impossible. American proximity fuses made conventional air attacks against their fleet suicidal. American electronic jammers rendered Japanese radar increasingly ineffective. American bombers operated at altitudes and with defensive systems that resulted in unsustainable losses for intercepting fighters. But most critically, he continued, lowering his voice, intelligence strongly suggests that America has developed atomic phaser, weapons devices with destructive capability orders of magnitude beyond conventional explosives. The silence that followed was profound. Though rumors of the Manhattan Project had circulated among scientific circles, this was perhaps the first time the possibility had been presented so directly to Japan's leadership. You are certain of this? Asked General Korechika Anami, the war minister, and a hard-line proponent of continued resistance. I cannot be absolutely certain, Nakamura admitted, but the intelligence indicators align with theoretical possibilities. America possesses both the scientific knowledge and industrial capacity to produce such weapons. We have neither in sufficient measure. Admiral Soemu Toyoda, Chief of the Naval General Staff, spoke next. Commander, your analysis of the proximity fuse technology demonstrated America's industrial advantage. How would you characterize this new threat in comparable terms? Nakamura considered his words carefully. The proximity fuse revealed a gap in electronics, manufacturing, and application. An atomic weapon would represent a gap so vast as to place America in a different technological era entirely. We would be as samurai facing machine guns. The meeting continued for hours, with Nakamura answering technical questions with increasingly direct responses. The time for face-saving equivocation had passed. Japan stood on the precipice of annihilation, facing an opponent whose technological advantages had become insurmountable. As he departed the bunker that evening, Nakamura found himself walking alongside Minister of the Navy Mitsumasa Yonai, one of the few senior leaders who had consistently argued for peace negotiations. "Your assessment confirms what some of us have argued for months," Yonai said quietly. "We face not merely a powerful enemy, but one whose industrial and scientific capabilities have surpassed ours by a margin we cannot overcome." Nakamura nodded. "The proximity fuse was the first clear evidence of this reality, Admiral. Had we properly understood its implications then, perhaps different decisions might have been made." Yonai's expression remained impassive, but his next words carried the weight of painful recognition. Sometimes a nation must recognize not just tactical defeat, but strategic obsolescence. The world has changed while we clung to old visions of warfare and national power. On the 6th of August 1945, Nakamura was at his mountain laboratory when news arrived of a new type of bombing attack on Hiroshima. The reports were fragmentary and confused a single explosion, unprecedented destruction, strange after-effects unlike conventional bombings. He knew immediately what had happened. The Manhattan Project had delivered its terrible creation. America's technological superiority, which he had first glimpsed in the proximity fuse, had culminated in a weapon that rendered all conventional calculations of military power obsolete. 3 days later, a second atomic bomb fell on Nagasaki. The theoretical had become devastatingly real. Japan's remaining industrial capacity, already crippled by conventional bombing and blockade, could not possibly respond to this new technological threat. On August 15, Emperor Hirohito announced Japan's surrender. The long war, which had begun with Japanese tactical brilliance at Pearl Harbor, ended with American technological supremacy, demonstrated in the most terrible way imaginable. Nakamura listened to the Emperor's broadcast from his laboratory radio, surrounded by the components of proximity fuses that Japan had never successfully mass-produced. These devices, once so mysterious and threatening, now seemed almost quaint compared to the atomic weapons that had forced Japan's capitulation. In the years that followed, as Japan rebuilt under American occupation, Nakamura found himself recruited for the nation's economic reconstruction. His experience with American technology and industrial methods made him valuable to a nation now forced to reimagine its future. During a meeting with American occupation authorities in 1946, he encountered a familiar face, Dr. Merritt Phillips, formerly of the Johns Hopkins Applied Physics Laboratory, who had led the proximity fuse production program. "Commander Nakamura," Phillips greeted him, extending his hand. "Or should I say Professor now? I understand you're teaching electrical engineering at Tokyo University." Nakamura accepted the handshake. Dr. Phillips: "Yes, I've returned to academia. There is much rebuilding to be done." Over coffee in the occupation headquarters, the two engineers, once adversaries, discussed the technological aspects of the war with professional detachment. The proximity fuse was a remarkable achievement, Nakamura acknowledged. "When I first examined a captured unit in 1943, I recognized immediately that it represented not just a weapon, but a demonstration of America's industrial and scientific integration." Phillips nodded. "It was a vast undertaking. At peak production, we were manufacturing over 40,000 fuses per day across multiple factories. The techniques we developed for quality control and mass production of electronics changed our industry permanently." 40,000 per day, Nakamura repeated softly. The number still seemed almost mythical. Our entire national output of similar electronic components was perhaps 2,000 per month, and with far lower reliability. Phillips studied his former adversary with professional respect. "You understood the implications better than most of your colleagues. From what I've heard, your technical assessment of our capabilities was remarkably accurate." "Understanding was insufficient without the industrial capacity to respond," Nakamura replied. "That was the lesson I could not make our leadership comprehend. Modern warfare is not merely about courage or tactical brilliance, but about systems of production and scientific application." As they parted, Phillips offered a perspective that would shape Nakamura's future work. "The technologies we developed for war have tremendous peaceful applications. Miniaturized electronics, mass production techniques, quality control systems. These can build consumer goods and infrastructure as easily as weapons. In the decades that followed, Nakamura became a key figure in Japan's electronic industry renaissance. The nation that had failed to mass-produce proximity fuses in wartime became a world leader in transistor technology, integrated circuits, and consumer electronics. The factories that emerged in post-war Osaka, Tokyo, and Kyoto employed the very techniques that had given America its decisive technological edge during the war. The gap that had seemed insurmountable in 1943 closed year by year as Japan rebuilt its industrial and scientific infrastructure with singular focus. By 1965, as Nakamura approached retirement, Japanese electronics firms were competing successfully in global markets. The proximity fuse that had once symbolized Japan's technological limitations had been succeeded by transistor radios, television sets, and early computers that demonstrated the nation's newfound capabilities. During a technology conference in San Francisco that year, Nakamura encountered his old American colleague Dr. Turner for the first time since before the war. Now both distinguished professors emeritus, they reflected on the technological transformation they had witnessed. "The proximity fuse seems almost primitive now," Turner remarked as they overlooked San Francisco Bay. "Vacuum tubes and mechanical switches compared to the solid-state electronics we have today." Nakamura nodded. Yet, it represented something profound, the integration of science and industry at a scale that transformed warfare. Japan could not match that integration in 1943, but we learned the lesson well. "Perhaps too well," Turner said with a smile. "My students all use Japanese calculators and transistor radios now. Your companies are redefining consumer electronics globally." The irony wasn't lost on either man. The nation that couldn't produce proximity fuses during the war now pioneered pocket calculators, transistor televisions, and electronic watches that demonstrated mastery of miniaturization and mass production. The proximity fuse taught Japan a painful but necessary lesson. Nakamura reflected. National strength in the modern age derives not from martial tradition or fighting spirit, but from scientific education, industrial capacity, and technological innovation. We rebuilt our nation on that understanding. As the two elderly engineers parted for the final time, Turner offered a handshake and a question. "If you had succeeded in replicating our proximity fuse technology in 1943, do you think it would have changed the war's outcome?" Nakamura considered this counterfactual briefly before shaking his head. "No. The proximity fuse was merely a symptom of a larger disparity. Even if we had somehow managed to produce them in limited quantities, the underlying industrial and scientific gap would have manifested in other ways." He gestured toward the Golden Gate Bridge, a symbol of American engineering. "What I realized in my laboratory in 1943 wasn't just that we couldn't match a specific weapon, but that we were fighting against an entire system of technological development and production that we did not possess. That understanding eventually helped rebuild Japan, but it came too late to change the war. In 1970, shortly before his death, Nakamura published his memoirs, including a detailed account of his work on the proximity fuse project. The book became required reading at Japan's technical universities, a case study in both technological assessment and the relationship between industrial capacity and national power. In its conclusion, he offered a perspective that resonated in a nation now emerging as an economic superpower through technological excellence. The proximity fuse that defeated our aircraft carriers in 1944 contained the DNA of the transistor radios and calculators that Japan now exports globally. Our inability to mass-produce those complex electronic devices during wartime revealed limitations that post-war Japan determined to overcome. The lesson we learned at tremendous cost was that national strength in the modern age flows not from martial valor or territorial conquest, but from laboratories, universities, and factories, from systems of innovation and production that transform scientific knowledge into practical applications at scale. In this sense, Japan's post-war economic miracle represents the final vindication of a truth I glimpsed in my laboratory in 1943, studying a captured American proximity fuse. Technological capability, once established, becomes the foundation of national power in all its forms. The nation that masters the creation and application of technology shapes not only its own destiny, but the future of humanity. The proximity fuse that had once symbolized Japan's technological limitations became, in retrospect, the catalyst for its transformation into a nation that defined technological excellence. The engineers who had failed to replicate American electronic warfare systems in 1943 built the foundations for Sony, Panasonic, Toyota, and Honda companies that would eventually challenge and sometimes surpass their American counterparts. The technological gap that Nakamura had identified through his analysis of a single captured weapon had been not just closed, but reversed in certain fields. Japanese electronics, once hopelessly behind American capabilities, became global standards for quality, miniaturization, and innovation. This transformation represented the ultimate legacy of those Japanese engineers who had studied captured proximity fuses in 1943 and recognized not just a weapon they couldn't match, but a future they needed to create. The nation that could not produce miniaturized vacuum tubes for war eventually pioneered integrated circuits for peace, turning technological defeat into the foundation for economic renaissance. The proximity fuse, in historical perspective, became not just an American victory but a Japanese awakening, a catalyst for a national transformation more profound and lasting than any military conquest could have achieved. From the laboratories where engineers had once struggled to understand captured American technology emerged a new vision of Japan's future, one built not on imperial expansion but on technological excellence and industrial precision. That future, born in the ruins of defeat, would eventually make Made in Japan a global synonym for technological quality and innovation, a victory of transformation more meaningful and enduring than any battle won or lost during the war itself. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.